Hi, everyone. Welcome to another GrowON event. I'd like to start just by asking the people people that are in person, if you could just turn your phones to silent, that'd be great, just to reduce any kind of distractions. My name is Fadi Al Daoud. I'm the greenhouse vegetable specialist with the Ontario Ministry of Agriculture, Food and Agribusiness, as we're now known as OMAFA. My co-host today is Abby Wiesner, OMAFA's greenhouse floriculture acting specialist. And we're here in person at the Ontario Greenhouse Vegetable Growers. So thanks very much to OGVG for generously providing the space. Just to remind people, the presentation will be recorded, but the Q&A afterwards will not be. Any kind of online questions, please put them in the Q&A, and we'll get to them after the presentation. So now I'd like to proudly acknowledge that Windsor-Essex region is on the land and surrounded by water, inhabited by Indigenous peoples since time immemorial. This territory is within the land honored by the Wampum Treaties, agreements between the Anishinaabe, Haudenosaunee, Lenni, Lenape, and allied nations to peacefully share and care for the resources around the Great Lakes. So I'd like to introduce our speaker today. Dr. Youbin Zheng is a horticulture professor at the University of Guelph with over 25 years of research experience in controlled environment agriculture plant production. He has traveled worldwide to study advanced technologies for Canada's CA plant production industry. His current research focuses on developing science and technology to efficiently and sustainably produce high-value plants such as strawberries, cannabis, vegetables, and ornamentals within controlled environments. Dr. Zheng's research team is particularly interested in horticultural lighting and root zone management, including growing media and fertigation. His extensive research has resulted in over 150 peer-reviewed scientific papers, more than 10 book chapters, and numerous extension articles and other scientific reports. Dr. Zheng is frequently invited to speak about his research at various forums globally. Thanks for joining us, Dr. Zheng. Please help me welcome Youbin to our meeting.
Thank you, Fadi, for the introduction. Thanks for inviting me here, and glad to see you guys here in the room. And thank you guys for being online as well. I will see how do I make this work. Fadi, how do I forward to another?
Yeah, just click on it.
Oh,
yeah.
Okay. Good. Yeah. So I'm going to talk to you on how to use light spectrum and spectrum combination to steer plants. When I say steer plants here, is meaning to change the morphology and sometimes also the color of the plants. So the plants can be edible and ornamental or medicinal. So I'm going to talk about some basic scientific knowledge on lighting and plants first, and then how plants respond to different light spectra and spectrum combinations. And then I will provide you with some examples on how to apply the knowledge in number 2 in controlled environments plant production, and then give you some take-home messages. I know even in the room, we got Xiumin Hao and lots of experts I see. I'm sure online, we have lots of experts on this. And I also, sometimes we have audience, the audience are beginners. So what I'm gonna do is I'm gonna try to make these understandable by anybody. And then so at the end of the talk, if every one of the audience can say, yeah, I learned 1 point and I will be happy, just 1 point, okay? So light, that's the sunlight You see here is from, we only measured from 380 nanometer to 780. So you can see we have UV, blue, green, and red light and far red light. The light intensity for sun lunchtime normally in this area is about a little bit more than 2,000 micromole per square meter per second. But of course, today we are not going to focus on light intensity. Light intensity, I can spend hours talk to you, use light intensity to steer plants. But today we're going to focus on light spectrum. So if you look at this one, light spectrum, normally from 400 to 700 nanometer, we call this photosynthetically active radiation. And then we have a little bit UV, a little bit far red here. So this y-axis is absorbance. So we have absorbance curve for chlorophyll A, chlorophyll B, carotenoids. So you can see mostly it's in the blue and red region. And if you look at this line, and it's the photosynthetic rate response to different light spectrum. And so at the green part, or the blue part, from 400 nanometer to 500 nanometer, and then in the red part, 600 to 700, it's the highest. Okay, plants use these two spectrum most efficient. So that's why in the past, at the beginning, when people made LEDs, they are blue and white and give you the Syngenta color just to make the light more efficient. But I already showed you the sunlight is, we have 4 spectrum. And when you grow plants, what light should we use? And then that's a very important question. One thing I want to mention to you is how plants sense the light and then to respond to light. There are many photoreceptors. The first one, if we look at the short wavelengths, which have higher energy. So the UV, plants have UV resistant locus. And then so this will sense UVB. And then UV can turn off shade avoidance and flavonoid biosynthesis. And then you have the krypton chrome 1 and 2. And this receptor is in charge of phototropism, DNA repair, and then also flowering. And these will sense UVA and blue. And you have phototropin 1 and 2. This will respond to blue and UVA and for the phototropism, stomatal opening, and also chloroplast movement. The chloroplast movement is sometimes, if you have a leaf, you have different light level, and then the chloroplast will move away from the light if there is not enough light, or move towards the light to block the light. And then also you have ZFL. This protein family controls flowering, stomata opening. Then you look at the red part, red and far red part is the phytochrome. Phytochrome is responsible for the seeds germination, inhibition of inundation, shade avoidance, which is make plants more elongated. We'll talk about that later. And also chloroplast development, leaf expansion and flowering. I'm not expecting you to remember all of these, but for people who really into it and also want to find out how plants respond to light, especially the light color, you can look into this because quite often it's complicated and then also confusing. I will talk to you a little bit more about it. For example, sometimes the blue will stretch plants, and sometimes blue will make plants more compacted. Why is that? And then because all of the photoreceptors, but they are not only response to the light color, but they also response to light color differently at different light intensity. And then also, of course, the environmental conditions can control them as well. And so this process, how plants respond to light, is called photomorphogenesis. And then we can, if you know photomorphogenesis, and then you can use light, manipulate light to steer your plants, to grow the plants the way you want them to look. So first, we'll look at blue light. Blue light can stretch, reduce, or promote stem elongation. And in the past, I will talk more about this. In the past, in the textbook, it's all reduce elongation to make plants more compacted. But our recent research, we've done loads of research and found that pure blue is able to make plants more elongated. And it can make leaf thicker and darker and increase anthocyanin to make plants look different color, promote rooting, flower initiation, and can open stomata and a bunch of other things blue light can do. And so let's first look at reduce or promote elongation. If you look at textbooks, almost all of the textbooks say blue can make plants more compacted, which is reduce the elongation. And this was mainly due to in the past, when people were doing research on lighting, they use filter. So if you use filter to create that blue, you always got some contamination. You cannot filter it out 100%. Only until recently, the LED technology come into play, we are really able to provide blue as blue. So in the past, some of the research is limited to that. The reason that most of the research found that blue can make plants more compacted is because the more blue, if you have red and blue, the more blue you have in your light, the plants are more compacted, okay? So that's why if you, normally you see the plants get, elongation get reduced. But our research, we use LED. So if you use LED, you can produce pure blue, and then pure blue can get the plant stretched. So it's the other way around. And then I will show you, a few years ago, we did this research. We grow plants, arugula and mustard, under red, just pure red light, at different light intensity from 20 micromole to 650 micromole. And you can see that the plants under lower light intensity, they are taller. And then when you increase the light intensity, it's more compacted. This is under red. Under blue, it's the same, okay? But one thing, if you compare the blue and red, blue probably stretch the plants a little bit more. And of course, here is not that obvious. I can tell you, I will show you more example down the road is that if you use lower intensity, provide pure blue light, you can really stretch plant. How do we use this knowledge? You can use it for growing microgreen. Microgreen, we know that you grow microgreen, it seeds germinate. 2 to 3 weeks, you have to harvest. If you harvest, use human and use scissors to cut it, it's too labor intense. So people trying to use machine to harvest. But if you use machine to harvest, if the microgreen is not tall enough and it's hard. So we did some research. We grow the plants and then switch to pure blue just for a few days, and plants stretch tall enough, and then you can harvest it. So that's one example. You can use pure blue. And another thing I want to show you here is that there's one grower. They grow bellflower campanula a lot. So they propagate this by taking cuttings. And then they want to grow plants indoor and use electrical light, only no sunlight. So they want to produce lots of cuttings. But at this moment, they are using use scissors to take the cuttings, so which is hard. So use blue, we thought what we can do is to design a light recipe. So we grow the plants first, use pure red, because red can increase branching, because you want to take cuttings, so you can use red. So we used red to grow the mother plants first, and then we got more branching. And then after that, if you want to use a machine to harvest it, it has to be tall enough. And then we give pure blue for the second stage. And then of course, the plants may look a little bit slim. So we use red and blue again to make the plant stronger. And then so they will look normal, but then at the same time you have more branches and taller. You can use a machine to harvest. So the total light we used is the same, and comparing to the red and blue as control. And so here, what we used for the concurrent lighting is red and blue, 85% red and 15% blue. And then here is the dynamic lighting, red first and then blue, and then red and blue. We use 24 hours photo period. And here is the result. At the beginning, the first 2 weeks, just red and compare with red and blue. You see the height of the plant canopy were similar. And then you switch to pure blue, the plants start to increase. See here? And then we finish the plant here with red and blue. Yeah, so that's how, if you understand how plants respond to different spectrum, that's how you can play around. Yeah, so that's just give you one example how we play around the lighting to achieve what we want to achieve. Blue can also make the leaf thicker and darker, and then also increase anthocyanin and some other phytochemicals. To know this, why it's important is that if you are growing baby greens or some other leafy greens, if you want to make your salad crunchy, you can make it thicker. And then also, if the color, because sometimes the color, certain group of people like to buy vegetable different color. If the darker, the leaf are darker, they feel it's more nutrient packed, which is true, because if you increase blue, you can increase anthocyanin and some other things. Those are the nutrient compounds as well. And then so here you can see a good example that lettuce, the same lettuce grow under red, it's green, and under white light, which have blue and red, and it's a little bit purplish. And under blue, that's the color you got. Yeah, so it's very attractive. There is another research by Owen and Opis, 2015. What they did was they grow lettuce, but before harvest, they gave the lettuce different light. The control was, the plants were growing in a greenhouse. You use solar light, and then they have white LED. The total light intensity was 4.5 micromole per square meter per second. And then they also use HPS at 70, and then it's red 100. And then my screen blocked mine. And this, I believe this is 50-50. Is that 50-50? Yeah. Yeah. And then you, so here is pure blue, but with 25, 50, and 100 micromole per square meter per second. And then you can see just after 3 days, only 3 days, this, I cannot get rid of that. This red become, the lettuce under red turn into red purple, and then blue as well. But the longer you expose the plants to this light, it's getting darker. Yeah. We will move a little bit here to trying to make the screen bigger so I can see the whole screen. Maybe not, because the zoom. That's okay. So this is for vegetable, edible. But you say, well, how about ornamentals? Ornamentals, you are also be able to use light to change the ornamental plants to make them look differently. For example, the same group did the same research on the blue. So 3 days later, exposed to all these different colors. Blue, this is fountain grass. Only 3 days, the fountain grass become a little bit purplish. And then the longer you expose to, the deeper the color is get. See, it's the same cultivar, but you grow them just before you harvest them, before you ship them, just change the light color will bring your product different color and to attract people to buy your product. And so there are lots of things you can do, use blue light to steer your plant. And just for the irrigation part, recently we done a review. Dr. Kong done a fantastic job, put together this paper is magic blue light, a versatile mediator of plant irrigation. If you search this title, you are able to get on internet for free. It's published. So if you look at the blue light, we just focus on the blue light here. How are you able to use blue light in your plant's production? When it's used for soil source lighting, you can use this to promote plant irrigation. For example, if you are doing tissue culture for producing eggplant, you can use blue light. You can use blue light to increase the height of your rootstock plants for grafting. And mother plants, I already showed you how do you use that. If you are producing cut flowers, if you want the stem to be longer, you can just use blue light. But blue light, when I say blue light here, is not you have to use it all day. You can just grow your plants the same way as you normally grow, but end of the day, you can give blue light just a couple of hours. It depends on the plant, the length, either a few hours or a couple of hours. You can get your plants, they stay much longer. And microgreen production, I already mentioned. So there are tons of things you can play around just by manipulating light. And blue light can initiate, help initiate flowering. And for example, we did this research by growing mums in greenhouse during late fall when the light in our greenhouse is a little bit, the photo period is short and then light was not that strong. So we used blue light, only 14 micromole for half an hour to 3 hours, just at the end of the day. And then you got more buds, and then also the plants are taller. I'm not saying when you grow chrysanthemums, you want your plants to be taller here. It's just we prove that you can make your plants flower more and then grow taller. And then also some other people's research showed that you can use blue light in the night, just extend the blue light so you can get your chrysanthemum to grow stronger, longer, just by provide blue light. And then I don't know anybody growing cannabis. Maybe somebody online are growing cannabis. We know cannabis, normally you want them to flower, you give them 12 hours dark period. But then our research demonstrated that the more light you give to cannabis, the more higher yield you get, okay? So one thing is that based on the chrysanthemums, can you give cannabis more blue light during the night? And then you can get them to bloom, they don't reverse back, and then you go higher yield. But no, you cannot do that. You see, so sometimes it's different species, they respond differently. So you can get cannabis to flower by providing them 12 hours dark period. And then if you give them blue light, if you extend the photo period, even use blue, the plants will come back, get into the veggie stage again. So, but chrysanthemums, they don't. See, so just keep in mind that different species respond differently. And then again, Dr. Kong done a very nice literature review and diverse flowering response to blue light manipulation. So again, this one you can search on the internet. There, we put lots of tables. We searched all the world, the history, find all of these response, how plants flower response to blue light. So even I'm not talking about your crop, probably you can search this paper. Maybe your crop is inside, okay? And then UV. And you all know that we have UVC, UVB, UVA. UVC is between 100 to 280 nanometer. This is the one you use to kill pathogens in water or in greenhouse. And then UVB is from 280 to 315. This can affect secondary metabolites accumulation, reduce cell and stem elongation, increasing branching closed stomachs, cause stress, control powdery mildew. And then you have UVA, which can affect secondary metabolites. It's just like that blue light can increase anthocyanin, and it can make the leaf and flower color different, mostly a little bit darker. And UV really, again, if you know enough, your plant enough and UV enough, you can use UV to increase your food nutritional value by apply UV. And another thing is that because plant response to UV sometimes is a stress response. So if you give your plants UV, they feel they are under stress. So they will produce certain second metabolites to against this stress. So some people are using UV. For example, if you are propagating, you can give your plants, young plants, UV light just to stress them a little bit before you transplant. And then they will be more resistant to drought stress and disease and insects, this and that. And UV can reduce powdery mildew. This is, we did this research. This is, you can see these are cannabis plants. In the 1980s, some people did research saying UV can increase THC. That was published. And then since then, people say, yeah, we'll use UV to increase THC. And so we did research because now cannabis is legal. You can use LED to grow plant cannabis indoor. And how do you use UV to increase THC or CBD? So we did this research by applying UVB from low intensity to high. And what we found was no, don't use UV in this case, because UV will make your plant smaller. And then also THC didn't increase. And we did another trial, found the same thing. I'm not saying UV will not. Maybe we just haven't found the way to apply to that yet. However, we accidentally found that UVB we applied really controlled powdery mildew. So those plants were growing in one room, same room. They are intertwined. The plants not exposed to UVB, you can see powdery mildew on them. And then when you have UVB, there's clean on the leaf, no powdery mildew. But of course, there's a trade-off. If you use it, your plants grow smaller. And then so that's something to take into consideration. Green is from 500 to 600. When I was doing PhD, I did lots of research on photosynthesis. My advisor, everybody at that time said, well, in the night, when you go and measure photosynthesis or respiration, have a green light, because plants are not response to green light because the curve I showed you, red, blue and red from that curve. And so we did that. Everybody did that. But now more and more research found green are useful. Quite often, if you add green to red and blue, your photosynthesis increase and your plants grow bigger. But of course, also green is important for us to make LED white LED, because if you don't have green over there, the light doesn't look green. And also in the past, people say plants look green because they reflect more green to your eyes. Is that true? And our research, Daniel's research, Daniel is in the room. So basically, grow plants in greenhouse, eggplants in a greenhouse. And then he measured the light spectrum, and that's on the top of the eggplant. And then 20 centimeters under, and then 40, 60 down. So that means, this light, the light source coming here through the leaves, that's the blue. So blue, red, we know they get absorbed by leaf, and then they were doing photosynthesis. Green, see, if they are all reflected, useless. they would increase the ratio, but they will not, either on the sunny day or cloudy day. But one thing though, that's far red light. You see, the deeper you go under the canopy, the higher far red ratio. That's why far red is able to make plants to have shade avoidance. On the forest, the leaves will filter sunlight, but absorb blue, red, in this case, green as well. But they will let far red to penetrate. So the ratio, red-far red ratio will change. So the plants sense that more far red, I must under shade. Somebody is above me. I have to grow fast, tall, and then be able to survive. Otherwise, I'm going to be killed. So you can use this knowledge by using red-far red ratio to steer your plants to grow stretched. Yeah, so I'm going to talk about that a little bit more later. So red light is between 600 to 700, is effective in preventing short day plants flowering. If you grow short day plants, like chrysanthemums, they will flower like in winter time. But if you want to keep them vegetative as mother plants, you don't want them to flower. What you do is that you can give them during the middle of the night, just give them a little bit of red light, very low level red light. That will keep them vegetative, not producing flower. But if you want to promote flower in long day plants, you can use red light to extend the photoperiod. You can also use red light to stimulate roots formation and a bunch of other things. But I want to talk more about far red. Normally people say far red is between 700 to 800 nanometers. I already mentioned to you that the far red ratio, I'm going to talk about that again because it's very interesting. Far red, and as you guys know, in the past, it's not included in the photosynthetically active radiation. It was only from 400 to 700. But now more research, especially now we have LEDs, people find far red, they are useful for photosynthesis. One is that they will help produce or fix more carbon if you provide far red. And another thing is that if you provide far red, the plants, they feel that somebody is above them. So their leaf become thinner and then bigger, so they can catch more light as well. So overall, far red can help plants grow bigger. So that's the innovation I already mentioned. So also make the plants thinner, leaf thinner, and leaf bigger to catch more light. But it will reduce branching. So if you are growing mother plants, try not to provide too much far red, because that will reduce the branching. Because the plants, when they are under far red, or the red-far ratio is low, more far red, and then they just want to survive. They don't want to produce that many branches. They just want to grow taller than your neighbor. So otherwise, you're going to be killed. And then it also promotes rooting in cuttings if you are rooting your cannabis or some other ornamental plants. And it can reduce morphological abnormality under 100% artificial lighting environment. Quite often when you grow plants in growth chamber and you see the leaves have bumpy leaves, this and that, those are abnormal phenomena. So if you provide a little bit far red, then it will correct this type of disorder. And I already talked about this. So I'm not gonna repeat it. But again, just keep in mind your plants under level, under canopy, the far red ratio, far red is to red ratio is higher, but green really plants are using green. You can see from here. This is real world data. Yeah, Daniel. This is published on Hot Science, so you can search for this article. And so the red far red ratio, if you look at our sunlight, most of the time during the day is 1-to-1 ratio. But at the end of the day, you go higher far red, less red. The ratio is changing. And so this is very important to know, because if you have higher far red ratio, your plant's gonna stretch. And so I will show you some of our research findings as examples. So here we grow plants under fluorescence light. So you see they are a little bit UV, blue, and amber red, and then a little bit far red, And then we also used LED, blue, red LED with far red. Okay, so the ratio of the LED, red far red, was 1-to-1. Fluorescence was close to 15. So the far red is tiny little bit over there. And so you can see the same plant grow under the same condition, just different light. One huge petunia, one tiny little one. And Calabricoa, it's the same thing. Same thing. That's why you can use lights to steer your plant. It's magic. It's like, yeah, it's just exciting. And then also you see the plant, the color even changes. Yeah, that's the geranium you normally see. But of course here, I'm not saying because the lower or higher red, far red ratio caused this color change. It's more probably there was UV as well in fluorescence light, but LED there wasn't, only red and blue and a little bit far red. So the light spectrum really play a huge role in plant growth. Here was one plant grow in greenhouse. So you have the natural sunlight. Here, this one was growing under HPS. That's, you see, the leaf growing curved downward. And then also you have these bumpy things here. And that's what I was talking to you about, that far red. If you provide a little bit far red, you can correct these abnormal phenomena. Especially this is important for vertical farming growers, for certain of your plants. Of course, probably for baby green doesn't matter. Maybe this is tastes better. But for certain plants, if you want your leaf look normal, and you need to provide far red. I don't know anybody grow Easter lily or not. Easter lily, because it was grow before Easter, and it's normally we have short, not enough light. And before Easter, they would put Easter lily into boxes. If the Easter lily is too tall, they are useless. You cannot put it into boxes. So because the box is a certain height, it's easier for shipping to supermarket to get sold. But if it is a little bit taller, you cannot fit in, throw them into garbage, okay? So quite often is that you don't want your Easter lily to grow too tall. So either use growth regulator, or Dr. Theo Blum is use cold water to water the plants to make them short. And there's another thing you can do is black out, like in a greenhouse, because at the end of the day, the far red ratio decrease. That's the plants say, oh, I'm on the shade condition. I have to stretch up. That's the time they stretch. But if you block that during the evening, and then the plants will be more compacted. So you see here, blackout. And then also we thought, well, blackout, you still have to black out. There are work to do. How about you just use the LED, red LED? And then you will change the far red ratio by providing far red. Yeah, that's, again, you can just do that to keep your plants more compacted. And different light spectrum will have different impact on plants. So this one, again, you saw this photo, but actually that trial, we were growing plants under sunlight. And then at the end of the day, either give them blue or blue-red LED, but add a little bit far red. For chrysanthemums, if you have blue-red over there, they don't flower. But then because the far red is added, it's increased the height. For geranium, and this is short-day plants. And those plants, some of them are facultative long-day plants. And so if you provide longer photoperiod, red, blue, even a little bit far red, the far red just make them stretch, but they still flowered. Yeah, so you see different species respond to different spectrum differently. And here again, you see we have 4 different species here. We grow these plants under pure red, pure blue, or blue and red. And blue-red add a little bit far red. So you can see that, as we mentioned before, that blue can stretch plants. And if you have red add a little bit blue, the more blue you have, the more compact the plant will be. Yeah. But if you provide far red again, then hopefully I didn't make a boo-boo here. How do I do? Oh, good. Thank you, Fatty. So again, it's so interesting. Just play the spectrum a little bit. The same plant will be different size, look differently, and flower differently. And Kubota's research already also showed that you can provide, at the end of the day, just provide 6 micromole per square meter per second far red. For the blue and red light LED, you can stretch your plants by this is tomato transplant, just by provide a little bit far red, your plant will be stretched. This is important, especially if you are grafting your tomato plant, because a certain time you want your stock plants to have that height. And then say, yeah, tiny little bit. For 3 minutes, for God's sake. 3 minutes. That's short. And your plants just doubled the length. Yeah. Of course, different species respond differently. Here, I will go a little bit fast. That's fluorescence. That's 100% red, 90% red, 10% blue, 50-50 blue-red, 75% blue, and 25% red, and then pure red. You see this petunia. So the height are different, and there were treatment effect. And then this is another plant species, marigold. There were treatment effect. But for geranium, and this Calibrachoa, we didn't see any treatment effect. So different species would respond to spectrum differently. And now, this is a question for you guys. This is these are two cannabis plants. The left-hand side is more compacted, dense. It could be one type of cannabis. The right-hand side plant is more open. It's tall. So normally when you grow plants, cannabis plants during the vegetative stage, you want to build your plant to the desirable size and shape. You want them to be right size and strong, good structure. When I say good structure is that you may not like to have the one on the left because the air even cannot go through it. You grow loads of plants in your room. If you have a plant compacted like that, probably you will have powdery mildew or some other disease. So you want the plants to be a little bit open. Okay, so my question for you is based on my talk here, what light you can use to make that plant on the left more open? You can use blue, pure blue, at the end of the day for a few hours, the plants will be stretched. Or you add some far red, just trying to play that red-far red ratio, yeah? And then, of course, you also can use light intensity. So all this light intensity and spectrum you can use as a combination to steer your plants the way you want them to be. You know, genetically, sometimes is we just have it, and nothing you can do about it. But then we have light as a tool to steer your plants the way you want them to be. And then we want to have certain number of nodes. And then, so if you want them to have nodes, more nodes, far red will reduce the branching the node. So yeah, I want to stretch them a little bit, but then I want to have more nodes. And then you may use different light at different stage, you know, like we did with the companion mother plants for cutting. So that's the end of my talk, or close to my end, to the end of the talk. So there are some take-home messages. Hopefully, that the messages will make sense to you guys. Is that different genotypes and even the same plant at different stages can respond to light spectrum differently. I gave you some example. You saw that. Look for published results or conduct your own research to find out how your plant responds to light. And then you can use light to steer your plant. There are loads of publications in the past 10 years you can dig into. But I'm not saying your crop is included over there. But if your crop is not included or you want to do more things, do your own research. I'm open to do research with you guys as well, especially if you are a Canadian company. Our government is really good. In this part is better than lots of other countries because our government is strongly supporting our research. Say quite often is the company, if you want to do research, is going to cost you $100. If we tap into the government, you need to pay some as seed money for us to get the government money. But then after the tax return, all of this, you almost paid. It's almost the research is free for you. So let me know. I can help you do this type of research. If you do not know that much about how your plant responds to light spectrum, then buy white LED. That's safe. if you know well how your plant responds to different light spectrum, and then you also like to play around to achieve the best goal, as I showed you some of the examples, and then you may like to buy multi-channel adjustable LEDs. So that will give you more room. Say, hey, this time I want to have this combination, spectrum combination. The next stage, I want to do this and that. But if you don't know that much, just simply buy white LED that look good, and you can see they are diseased or not. And for supplemental lighting during the day, light spectrum is not that important, really. So for supplemental lighting, we found that, yeah, you can change the light spectrum as much as you can. Quite often is blue and red is good enough because you have sunlight and overwhelm the whole thing, okay? But if you grow plants as soil source and or to extend day length, and then the light spectrum is very important. And then I would like to thank the lighting companies, Plus Light, Heliospectrum Fluence, for providing me with these lighting fixtures. Otherwise, I cannot do this research. This research, some of them I mentioned here, were done by my two brilliant research associates, Dr. Yun Kong and David Llewellyn, and then also my brilliant graduate students, including Daniel here in the audience. And then of course, I always like to do research with greenhouses. So you see lots of greenhouse here. They support my research, and Koha, NSEC, all these funding agencies. And then also thanks for Omafra for organizing this. So give me a chance to have a conversation with our growers and lighting suppliers. And I would like to thank you all for being here. And I guess now is Patty's turn. Thank you.